Good evening, student. Myself Neeraj Pandey, and yesterday we discussed about different type of complex compound, cationic, anionic or neutral. But today we discuss about different type of another topic which is related with the coordination compound. Let's start. Our first topic is coordination polyhedron coordination polyhedron. Actually, the spatial arrangement of ligands with central metal ions is called polyhedron coordination polyhedron It means that when ligands attach with central metal atom, then it show a spatial arrangement with central metal atom, by which we can easily calculate the type of structure of any coordination compound or complex compound. On the basis of coordination number, we can easily calculate the structure of coordination compound or complex compound. You also know the total number of ligands is equal to coordination number, and this coordination number give an idea about structure of the compound or complexes, and we can easily understand with the help of example. If total number of ligands is equal to 2, then its coordination number also 2, and the structure is linear like CON twice. Similarly, if the total number of ligands is equal to 4, then coordination number also equal to 4. But in this situation, complexes may be tetrahedral, and example is PT-NH3 tetra. In this complex 4 ligands NH3 ammonia directly attached with the platinum, then it show tetrahedral structure. If the total number of ligands is equal to 4, then coordination number also equal to 4, but complex is square planar, square planar, because in this complex, like platinum CN4, 2 negative charge, NiCl4 is good example of square planar complexes. If number of ligands is equal to 5, then coordination number also equal to 5. In this situation, the complexes may be trigonal, bipyramidal. Similarly, if any complex have 6 number of ligands, then its coordination number also equal to 6, and it show octahedral arrangement of the complexes, like FeCN6, 4 negative charge. On the basis of metal ligand attachment in the space, give an idea about this type of geometry which is present in complex compound. After discussing the total number of coordination number and total number of ligands which is equal to one another, and it give an idea about the structure of complexes, we can discuss different type of structure of the complex compound, and we can also write the geometry of complexes. Like if En twice attach with platinum, it means ethylene diamine, like PT NH2 which is directly attached with methylene group, and 2 methylene group contains 2 NH2 group in their structure, and its name ethylene diamine. It have 2 donor atom and also NH2 when donate their lone pair of electron, and both are connected with the CH2 and CH2, then this structure is linear. This structure is linear. Similarly, some compound which show trigonal structure in which 3 ligands are present, it show this type of structure. Some compound have tetrahedral structure. In case of tetrahedral structure, the complexes show this type of geometry. In the complex, here sp hybridization, here sp2 hybridization, and here sp3 hybridization is possible. But in case of pentagonal bipyramidal structure, in which there are 3 and 2 structure, in which pentagonal bipyramidal structure of the compound, when combined with one another, then it form pentagonal bipyramidal structure. In case of octahedral, when metal have this type of structure, in which here it shows this type of representation in the complex and give an idea about octahedral complexes along x, y and z axis. When 6 ligands are attached, each corner of these like Cn minus Cn minus Cn minus Cn minus Cn minus Cn minus, and it is Fe for negative charge. In this complex, Fe attached with the 6 cyano group, therefore it show octahedral structure. After discussing the different type of geometry in complex compound or coordination compound, we discuss about the EAN, effective atomic number. Effective atomic number, which is indicated by EAN. Actually, EAN, we can explain it in very easy way, that the total number of electron of central metal atom or ions, total number of central metal atom or ion with gaining electron from ligands in the bonding of complexes. The total number of electron present in any central metal atom which is gaining by the ligands and also which is present toward the central metal atom give an idea about the EAN. This effective atomic number was firstly given by Sidwick. It is given by Sidwick. If any compound have total number of electron toward the central metal atom which is also taken by the ligands, if equal to inert gases, atomic number of inert gases, the EAN number of electron is equal to the total atomic number of inert gases, then these complexes follow EAN rule and diamagnetic in nature. If any ligands and central metal atom when connected with one another and total number of electron toward the central metal atom is equal to not equal to atomic number of inert gases, then it does not follow EAN rule and also show paramagnetic nature. Remember it. We can explain and understand with the help of example. For example, CN4. In this complex COCN6, not 4. In this complexes where firstly if we know about the formula of EAN, then we can easily explain what is the effective atomic number of these complexes. EAN is equal to Z minus X plus z minus x plus a into y, a into y, where z is equal to atomic number of central metal atom, x is equal to oxidation state, a is equal to number of ligands, y is equal to number of electron pair given by ligands. In these complexes, the atomic number of cobalt is equal to 27 and oxidation state of cobalt, if we does not know what is the oxidation number of cobalt, then we can't explain what is the EAN. In this complex, if we not know the oxidation state, then we can calculate. In case of cobalt, the oxidation state of cobalt is equal to, if oxidation state of cobalt is equal to X and total number of ligands is equal to 6 and it give 2 negative charge with 1 negative charge by each cobalt atom and it is equal to -3, then X is equal to -3 plus 6 is equal to +3, then oxidation state of cobalt is equal to +3. Thus, in this complex, X minus 3 plus total number of cyano group is equal to 6 and total number of electron pair given by each cyano group is equal to 2, then it become 24 plus 12 and 12 plus 24 is equal to 36 and 36 is equal to this number is equal to krypton, whose atomic number 36, and krypton is a inert gas. And we also know that if the effective atomic number of any complexes is equal to the atomic number of inert gases, then it follow EAN rule and diamagnetic in number in nature, diamagnetic in nature. If we try to know another EAN rule of the complexes, then we can take other example. For example, if we take NiCl4 2 minus In this situation, EAN of nickel is equal to total atomic number of nickel minus oxidation state is equal to 2 plus 2, and it have 4 ligands. Each ligands donate 2 electron in the form of pair. Then it become 26 plus 8, and 26 8 is equal to 34. But the 34 number never contains any inert gases. It means that this EAN is not equal to atomic number of inert gases, therefore it is paramagnetic in nature and does not follow EAN rule. Another example, like Fe, H2O, Fe, hexa, 3 negative charge. In this situation, the Fe whose EAN is equal to the atomic number of iron is equal to 26 minus oxidation state is 3 plus total number of ligands 6, and give each ligand 1 lone pair of electron minimum or negative charge. In this situation, it become 23 plus 12, and it is equal to 35. It is never follow EAN rule, because the EAN of iron Fe, H2O6, 3 plus, not minus, 3 plus is equal to 35, and 35 is not the atomic number of any inert gases. But in case of Fe, Cn6, 4 negative charge. In this complex, the oxidation state of iron is equal to plus 2. Therefore, EAN of iron is equal to 26 minus 2 plus 6 into 2 is equal to 26 minus 2 is equal to 24, and 24 plus 12 is equal to 36. This complex follow EAN rule because 36 is the atomic number of krypton or inert gases, and it is diamagnetic in nature. I hope you betterly understand how we can easily understand the EAN of the complex, effective atomic number of the complexes. After this type of discussion, we discuss about another topic, and topic is homoleptic and heteroleptic complexes. What? First is homoleptic and heteroleptic complexes. Homoleptic complexes are those in which same types of ligands are present for example NiCl4 COCN6. In this complex both the ligands in both the complexes are same Cl. All the ligands is Cl and all the ligands is Cn. If ligands are similar, not another, then it is known as homoleptic. Similarly heteroleptic complexes are those which have different types of ligands. For example FeCN4Cl2 2 negative charge, COCl2 NH3 tetra and PTH2O tetra NH3 twice 3 positive charge. In this complex ligands are different type. If there are more than one type of ligands are present, then it is known as heteroleptic complexes. I hope you betterly understand what is homoleptic and what is heteroleptic complexes. After this type of discussion, where we discuss homoleptic and heteroleptic complexes, one topic which is more important for your examination viewpoint is nomenclature of coordination complexes. There are different type of rule are present by which we can easily write the name of coordination complex, in which first rule is firstly we write the name of ligands. Firstly we write the name of cation. Firstly we write name of cation, followed by anions. Firstly we write the name of cation followed by anion, like K4 FeCN6. In this complex potassium is cation, because when we dissolve these complexes in the water, then it become 4K plus FeCN6 4 negative. This complex act as anion and potassium act as cation. So firstly we write the name of cation followed by anion. No matter cation may be present right side or left side. For example, if we take NiCl4 or NH3 tetra, NiNH3 tetra and SO4. In this complex NiNH3 tetra become positive complex, act as cation, and SO4 act as anion. So firstly we write the name of cation. It is the first rule for the nomenclature of coordination compound. Second rule, if it is first rule, and second is if we write the name of coordination sphere, then firstly we write the name of ligands. Firstly we write the name of ligands. For example, FeCl6. In this complex firstly we write the name of chloro, means chloride ion, because chlorine is ligands. COH2O or NH3 hexa. In this complex firstly we write the name of NH3 or ligands. Next point indicate that if more than one type of ligands are present, if more than one types of ligands are present, then there are two ways for the nomenclature of ligands. If more than one types of ligands or more than one ligands are present, then we discuss firstly how we write the name of ligands. Listen. First point is that if ligands is present more than one number and all are similar, then we prefixes use di, tri, tetra, penta, hexa before the name of ligands. If more than one types of ligands are present, then prefixes di, tri, tetra, di, tri, tetra, penta, hexa etc are used. etc are used. Similarly, if more than one types of organic ligands are present, then we used prefixes bis, tris, tetrakis, pentakis, hexakis, instead of di, tri, tetra, penta, hexa, etc. But if organic ligands are present, organic ligands means like ethylene diamine, ethylene triamine, diethylene triamine, triethylene tetraamine, if these are present in coordination sphere in the form of ligands, then we use bis, tris, tetrakis, pentakis, hexakis, etc. But if inorganic ligands are present, then we use di, tri, tetra, penta, hexa, etc. For example, FeCN6 with K4, then its name is potassium hexacyanato or cyano, both name are, you can write cyanato, okay. Hexacyano or cyanato, iron second. These are the name of these complexes. Similarly, if nickel contains ethylene diamine in 2 number, then its name become bis means 2, ethylene diamine, nickel second, okay. This is the nomenclature of ligands when ligands are similar. Next point, if ligands are dissimilar, means more than one type of ligands are present in complex compound. When ligands are dissimilar, then we use the alphabetical order for the naming of ligands. For example, FeCN2Cl2Br2, In this situation, there are three type of ligands are present: cyano, chloro and bromo. Bromine, chlorine and cyano group are present in the form of ligands. But toward the alphabetical order, firstly we write bromo, then chloro and then cyano, and its name become dibromo, dichloro, dibromo, dichloro, dicyano ferrate second, dicyano ferrate second. After naming of ligands, it is also very important to know that if ligands are negative, not neutral, if ligands are negative like halogen, like cyano, like NH2 amino, then word halide, cyanato, amido etc are used in state of halide, in state of cyanide, in state of amine. Means we use O after replacing E from the ligands. But if ligands are neutral, then its name are never change. But if any coordination, another rule is that if complexes is negative, then we add ATE in the name of central metal atom. But if any complex compound are neutral, then the name of central metal atom are never change. For example, NiCN4 tetracyanato nickelate, not nickel, nickel become nickelate because it contains negative charge on coordination sphere. Its name become tetracyanato nickelate second. Okay, and you also change the name of other cation, like cobalt become cobalto, iron become ferrato, and aurum become aurato, silver silverate, and plumbate etc are used. It means that we change the name of central metal atom if it contains negative charge on coordination sphere. But if coordination sphere is neutral, then there is no change. We write the name of central metal atom as such, like NH3 tetra. In this complex, it is the positive charge contains or positive charge present toward coordination sphere, then its name is tetra amine nickel. Second, another rule for the nomenclature of coordination complexes that if any coordination complexes have negative charge, then when we write the name of central metal atom, then its name is also changed, but its oxidation state always write in coordination sphere, not coordination sphere, in bracket, and before the naming of oxidation state we use hyphen or minus in the bracket, but the oxidation state always write down in Roman number like first, second, third, fourth, etc. Next rule is that if any compound or complex compound have hydrogen atom in their ionization sphere, then we never write the name of hydrogen. We use IUM instead of ATE of central metal atom, like PtCN4. In this complex, tetracyanato platinum, not platinate, platinum are used, platinum, IUM word used instead of ATE. Platinate become platinum for the naming of hydrogen, but we never write the name of hydrogen, and then we use oxidation state, and which is equal to second. Okay, and if next point is that if any coordination compound have negative charge species or cation in their ionization sphere, then we write the name of anion as such, not cation, anion as such, like NH3 tetra, SO4 act as anion, and this complex act as cation. According to this rule, firstly we write the name of ligands like tetraamine nickelate second sulfate. On the basis of this, you can explain that if we write the name of anion which is present in coordination sphere, then its name are always write as such, there is no any change, but these names are placed after the naming the oxidation state of any complexes. Another rule is that if any complex compound have bidentate ligands, tridentate ligands, tetradentate ligands, But if complex compound have bridging ligands, for the naming of bridging ligands, bridging ligands, firstly it is very necessary for you that you know what is bridging ligands. Bridging ligands are those in which a ligands directly bonded with two central metal atom. If any ligands is present in between two central metal atom, then this ligands is known as bridging ligands. For example, CO, NH, CO, OH, H2O, 4, H2O, 4 and 3 plus. This type of example is example of bridging ligands, in which if ligands is present in between two central metal atom, two central metal atom contains ligands in between them. For the naming of this type of ligands, firstly we use the word mu before the name of ligands, and then we use mu another name of ligands. If ligands are similar, then mu word are used 2 times. If it is not similar, then word mu are used different type with the name of ligands, and then we write the name of another ligands according to alphabetical order, and we write the name of cation means central metal atom with their oxidation state. What is the name of this complex is that here 4 water molecule present both side, 4 here and 4 here. Total number of ligands of number of water molecule is equal to 8. Therefore it become octa aqua mu dash amine mu hydroxo mu amine mu hydroxo dicobalt third. It is the name of bridging ligands. Are you understand how we write the name of ligands? Bridging ligands are those in which ligands are present in between two central metal atom. I hope you betterly understand what is the nomenclature of coordination compound. If we know this type of rule, then we can easily understand that how we write the name of central coordination complex. Thank you so much, and we discuss another topic in our next lecture. Thank you so much.